All right, welcome to our Chapter 2 presentation. In Chapter 2, we're going to talk about atoms, the subatomic particles that make up atoms, and we're going to talk about radioactivity. So our outline for this chapter is in section 2.1. We're going to talk about atoms and their components. Those components are the subatomic particles that make up an atom. We're going to talk about the difference between atomic number and mass number. These numbers are going to be used to determine whether or not something is a radioactive compound. There are a lot of different radioactive compounds out there, and we're going to try to discuss the ones that are medically relevant for the most part. And that would include things that are dangerous to us. We're going to talk about, in section 2.3, we'll talk about isotopes and atomic mass. Isotopes are versions of the same element, some of which can be radioactive, some of which aren't. Some of them are very stable. We'll talk about, after that, in section 2.4, we'll talk about radioactivity and radioisotopes. In 2.5, we're going to discuss nuclear chemical equations. We discussed chemical equations in chapter 1, and in chapter 2.5, we're going to discuss the nuclear chemical equations. Slightly different from chemical equations. They're really easy to balance, not difficult to learn at all. We're going to talk about radioactive decay. Most of our radioactive isotopes are going to undergo a radioactive decay that involves breaking down over the course of half-lives. And if you're working with radioactive material, especially in the medical field, you might be working with people who are receiving radiotherapy for cancer chemotherapy. You might be working with, if you're in imaging, you might be working with radioactive materials in imaging. And if you have to dispose of that, or if you spill it, you'll want to know what's the half-life of this stuff. How long is it going to be around? Is it dangerous to me? So we'll talk about that. We're going to talk about radiation units, how we measure radiation exposure to people. We're going to talk about half-lives. And finally, we're going to discuss the medical applications for radioisotopes. So we talked a little bit about the elements in chapter 1, and now we want to talk about the things that come together to make something a particular element. So why are all hydrogen atoms hydrogen? Why are all helium atoms helium? And the answer to those lie in these subatomic particles that make up our atoms. So atoms are the smallest unit of matter that we discussed that make up the building blocks of our compounds, but we have even smaller units of matter that make up our atoms. And there's even smaller units of matter that make up the subatomic particles that make up our atoms. But for the purposes of this class, we're just going to go down to these three basic subatomic particles: the protons, electrons, and neutrons. Our protons and electrons are charged particles. Protons and electrons are going to give rise to all of the different chemical reactions that we'll discuss in this class, with the exception of the nuclear reactions in which neutrons can also be involved. For the most part, neutrons aren't really involved in most of chemistry, but they can get involved when we talk about nuclear chemistry. Protons, as their name would suggest, have a positive charge. Electrons have a negative charge. These two guys like to attract one another. In nature, opposites often attract, especially with charges. Also think about it in terms of, think of magnetic force. The positive end of a magnet is attractive to the negative end of another magnet. And so in chemistry, a lot of times we're going to be talking about the charge-charge interactions of different molecules. And this is going to give rise to a lot of the different chemical properties that we're going to see, especially in the human body. So as we start to understand how protons and electrons are arranged in atoms, then we can understand how they come together to form molecules based on these charge-charge interactions. We can then have interactions between molecules, and those can give rise to really cool things, like the lipid bilayer that makes up the cell wall. These charge-charge interactions can cause proteins to fold up into a specific shape into an enzyme. So this seems like really basic stuff. Why do I have to know down to the subatomic particle to understand medicine? And you really do, because a lot of the interactions in our body come down to these simple positive and negative charge-charge interactions that can occur between subatomic particles, atoms, and molecules. So it's really important to know the whole picture from the subatomic particle level to the cellular level to understand medicine. I went off on a tangent there, so let's get back to it. We mentioned that protons are positively charged, electrons are negatively charged. Overall, atoms have no charge for the most part. There will be some ions that have charge, but a neutral atom in its elemental state has no charge because the number of protons will be equal to the number of electrons. We can have different states, so we could have an ionic state of something where something is dissolved in water. So for example, salts, this might not be true. Something might have more electrons than protons or more protons than electrons. For example, sodium metal has an equal number of protons and electrons. It's in its elemental state, so it has no charge. But sodium ion in sodium chloride table salt has a charge. The sodium has lost an electron. It takes on a +1 charge. So like I said before, there are exceptions to all the rules. We just mentioned the rule that overall atoms have no charge because the number of protons is equal to the number of electrons. The exception is, if it reacts to form a compound, it may have lost an electron or gained an electron, and now it might have a charge. And that charge might give it a certain chemical property. So be aware that there are exceptions to the rules, and we'll talk about how atoms can share and give and exchange their subatomic particles to do chemistry. I'll show you a few pictures of an atom in a second, but let's just talk about the structure of it really quick. The protons and neutrons, remember the protons are positively charged, neutrons are neutrally charged, they don't have a charge. Those guys are clustered together in a real tiny little clump called the nucleus in the center of the atom. The nucleus makes up a very small portion of the space of an atom. Most of the space that an atom takes up is in the electron cloud. So the electrons are dispersed in this area throughout or surrounding the nucleus. So this area surrounding the nucleus contains our electrons. We call this the electron cloud. The electrons are constantly moving. They're very difficult to measure. Physicists have spent lifetimes attempting to calculate how electrons move around and determine how they interact with other atoms around them. Because if we can unlock these secrets, then we can better predict chemical reactions and how to manipulate matter. So a lot of this stuff that we're going to talk about are very simplistic models. They're not actually how electrons move, but they're models that were created by chemists decades or even centuries ago to try to understand how electrons move around in space and how chemical reactions occur. So keep in mind, these pictures make it easy to picture in our brain, but they might not be exactly how things occur on the subatomic particle size scale. Speaking of atomic size scale, what unit of measurement do we use to measure something as small as an atom? The unit of measurement that we use is called the atomic mass unit, or AMU. And AMU uses carbon because carbon is an easy thing to get your hands on in massive quantities. And so they use carbon as a scalar. So they use 1/12 the mass of a carbon atom is 1 AMU. And that's also equal to the size of a single hydrogen atom as well. The reason that they didn't use hydrogen atoms is because it's difficult to measure hydrogen because it's a gas. It's difficult to weigh. So we use carbon, and as we are going to see, most carbon atoms weigh 12 AMUs because they have 6 protons and 6 neutrons, and protons and neutrons weigh roughly the same. So a proton and neutron each weigh roughly 1 AMU. The mass of an electron is very small, so for all intents and purposes we ignore the mass of electrons. They're about 2,000 times less than that of a proton or neutron. So this figure shows us what happens when we zoom in down to the atomic level and then down to the subatomic level, what things would look like. So lithium metal is one of our alkali metals in the first column or group of the periodic table of the elements. And if you zoom down in on this, all of the lithium atoms are smushed next to each other. And one of the neat things about metals is the atoms are all stacked next to each other, but you can bend them or shift them. They'll move around a little bit. So while they're a solid and they retain a shape unless you apply a force to them, you can get them to slide around a little bit. It's one of the properties of metals, why it's flexible, malleable. So we use that to our benefit for a lot of different metal compounds. as we zoom in on just a single atom, we can see the nucleus here. So for example here, this is lithium. It's the nucleus. We have 1, 2, 3, 4 neutrons, and lithium has 1, 2, 3 protons as well. If you get out your periodic table of the elements, you'll notice that hydrogen is the first element in the periodic table of the elements, and the number of protons dictates what element you are. So if you look, hydrogen is number 1, helium is number 2, lithium is number 3 because he has 1, 2, 3 protons. So this would be elemental lithium. So he has 3 protons. We would expect that he's going to be neutrally charged. Each proton gives us a positive charge. Each electron gives us a negative charge. So if we have 3 protons, we have to have 3 electrons to make this a neutrally charged atom. The next thing I want to discuss is how electrons are organized in that electron cloud on the outside of the nucleus. So this is really neat because this allows us to determine how a chemical is going to react, or how an element is going to react with other elements or other compounds. So the electrons are organized in these energy levels. So these energy levels are represented by these rings. And so you can see here that lithium has 2 rings. The inner ring, if you look at lithium, sodium, and potassium, the inner ring holds 2 electrons. Now, if you take a look at your periodic table of the elements, you'll notice that the top row, the first row in the periodic table of the elements, has 2 elements in it. Each row of the periodic table of the elements represents one of these rings of electrons. So if you look, hydrogen and helium both only have electrons in their first shell, or their first energy level. Then as we go down to lithium, there is no longer any room in that first shell or first energy level, and so the electron is going to have to occupy the next energy level out. Now that energy level out is a lot bigger than the first energy level on the inside, so it can hold more electrons. So it can hold up to 8 electrons. And for the purposes of this class, we're only going to pay attention to the first 8 electrons that the rest of the shells can hold, but the rest of the shells can hold up to 18 until you get into the lanthanides. But for all intents and purposes, the inner shell can hold 2 electrons, and for this class, we're going to focus on every other shell is going to have up to 8 electrons. And this is going to give rise to what we call the octet rule, which is going to be really important later on. So if you look at the periodic table of the elements again, and the alkali metals, you take a look at lithium. Now if you go further down the line, you'll see sodium. So we just added extra shells. And in that outer ring, you'll still see that we only have 1 electron. And then potassium, as we go further down those alkali metals, in that outer ring, he still has 1 electron. So all these guys in the alkali metals all have this one little lonely electron in their outer shell. And that's going to be very important because these electrons in these inner shells are not going to be involved in the chemistry of these atoms. These shells are going to be shielded by these outer shells. These electrons on the inside will not be able to interact. So for all intents and purposes, kind of useless in chemistry. It's these electrons in these outer shells that are going to dictate how this particular element is going to behave. And so we'll watch a video when we get to class on the reaction of alkali metals with water, and I'm sure you can just Google that and look at videos in YouTube, and you'll see that they all behave the same with water with increasing intensity as you go from top to bottom of the periodic table of the elements. So we're able to predict, based on how many electrons are in the outer shell of an atom, how that particular atom is going to interact. So that is why this is very important to understand these shells. So I already mentioned this a little bit, but let's talk about this in more detail. If atoms of the same element always have the same number of protons. So for example, if we look at the periodic table of the elements, if you get your book out, open up your periodic table of the elements, all hydrogen atoms have 1 proton. Doesn't matter how many neutrons they have, they're still a hydrogen atom. So they can have a different number of neutrons, but it's the protons that count to determine whether or not that element is hydrogen. So hydrogen is number 1 on the periodic table of the elements. Number 2 is helium. Helium has 2 protons. Lithium has 3, and so on and so forth. You can just go from left to right, top to bottom of the periodic table of the elements, and you'll see as you go from left to right, the atomic number increases, and that's the atomic number is the number of protons. So atomic number and mass number are going to be 2 different things. Atomic number is the number of protons in an atom of any element, and that can be determined from the periodic table of the elements. So there's a little block that represents each element, and above the element within the block is the atomic number. We'll point that out when we have an example here in a future slide. So the atomic number indicates the number of protons present in the atom of an element. So working with the knowledge that we've already discussed here, let's use carbon as an example. A carbon atom has the atomic number 6. We know that that means that it contains 6 protons. It's number 6 on the periodic table of the elements. That means it has 6 protons. We also know that all atoms of carbon will have 6 protons because the number of protons dictates the fact that it's carbon. And we also know that because atoms in their elemental state are neutral, they don't have any charge, then we can determine the number of electrons that will be present in the cloud outside of that nucleus. So because there are 6 protons, we'll be able to attract 6 electrons. So this figure is just a review of what we've discussed so far. So we see a lithium atom on the left here, and you can count we've got 1, 2, 3 protons. Each one of those protons has a positive charge. And so because each one of those protons has a positive charge, it can attract 1, 2, 3 electrons, each with a negative charge. And that's what gives us an overall neutrally charged atom. We've got the same thing going on over here with carbon, except we've got 6 protons, each with a positive charge. And that means we can have 6 electrons, each with a negative charge. And that's going to give us a total charge of 0. So we are neutrally charged there. Okay, mass number is different from atomic number. The mass number is what we're going to use to determine what isotope of a particular element we have. Atoms can have different isotopes, and we'll give the definition of an isotope in just a second. The mass number is the number of neutrons plus the number of protons in an atom's nucleus. So, or protons plus neutrons, it doesn't matter which way you do that. Once we know the atomic number and the mass number, we can determine the element from the atomic number and the number of protons and neutrons in that atom. So for example, if I told you that we had an element with the atomic number 6, we would just get out our periodic table of the elements and we would count to number 6 on the periodic table of the elements, and we would know that that atom is carbon. When we write these atomic symbols, we'll put the symbol for the element carbon here. We put the atomic number in subtext here at the bottom, and then on the top we will put the mass number, and the mass number tells us that this is in particular carbon 12. We could also write this in this way. I mean, my handwriting is just as bad electronically as it is in class. We could write carbon 12. Now you could also have carbon with a different number of neutrons. So I could have carbon 13. So I'd have carbon, I have 6, and I could have 13 here instead of 12. This would be carbon with 6 protons and 7 neutrons. So the total, 6 plus 7, would give me 13, which would be my mass number. Again, mass number is the number of protons plus the number of neutrons. So this would be an example of a radioactive isotope of carbon, and this could be used in carbon dating. So we'll have some example problems in our handouts, and this is one way that we can solve for problems in which they ask you to determine the number of subatomic particles and the symbolic notation for a particular element. So if you're given the atomic number, we could find the element on the periodic table of the elements. Whether you're given the atomic number or the name of the element, we could find it on the periodic table of the elements. You can then determine or use the atomic number to find the number of protons and electrons. Remember, the atomic number is the number of protons, and if it's in its elemental state, then the number of protons, positively charged protons, equals the number of electrons that are negatively charged. Then we can use the mass number to find the number of neutrons. And we just remember that the mass number is equal, so we put mass number there, is equal to protons plus neutrons. So if we already know the number of protons from the atomic number, and we're given the mass number, we can just solve for the number of neutrons. Then we can write the element in symbolic notation. So, for example, if I told you that we had an element that had an atomic number of 1 and a mass number of 3, if you look at your periodic table of the elements, the first element with an atomic number 1 is hydrogen. We'd put a 1 down here because we said that was his atomic number, and a 3 up here because that is his mass number. And this would be hydrogen 3, also known as tritium, which is a radioactive isotope of hydrogen that's used in imaging. So just to review what we've just discussed, atoms of the same element can have different numbers of neutrons. We discussed that you could have hydrogen with no neutrons, hydrogen with 1 neutron, hydrogen with 2 neutrons. Not all atoms of the same element have the same mass number because they can have different numbers of neutrons. Atoms of the same element with different mass numbers are what we call isotopes. So isotopes can be indicated in 2 ways. We can use that symbolic notation in which we have the elemental symbol, the atomic number, and the mass number shown, or we can state the mass number after the element name. So for example, we could have carbon 12. If I wanted to use the symbolic notation for carbon 12, I would draw my C. I would put down my atomic number, which is 6, and my mass number, which is 12. So just to practice this, how many protons and neutrons does that have? The number of protons is equal to 6 because it's carbon. The atomic number is 6. That's my number of protons. How many neutrons do we have? My number of neutrons is 12 minus 6. So remember, our mass number is the number of protons plus neutrons. So 6 and 6 give us the 12 up here. And my number of electrons is going to be equal to my number of protons. Carbon can attract 6 electrons. Carbon 13 then is going to have 6 down here. Its mass number is going to be 13. So my protons are the same. I still have 6 protons. My neutrons have changed now. Now I have 7 neutrons. My electrons remain the same. It's not the neutrons that attract the electrons, it's the protons. Neutrons are neutrally charged, so that's not going to change at all. The only thing that's changing from one isotope to another is the number of neutrons. So in carbon 14, same deal. C6, 14, you would have 8 neutrons. Everything else remains the same, 6 protons, 6 electrons. So we've talked about atomic number and mass number. Now we're going to put those 2 words together and come up with a new thing called atomic mass. I don't want you to get confused between atomic number, mass number, and atomic mass. So let's describe what atomic mass is. There's a number below each element on the periodic table of the elements, and it's some big long number with a lot of points past the decimal for the most part. In your periodic table of the elements in your book, it goes to the hundredths column there. So depending on what element you're looking at. So take a look at carbon for me. Carbon below the C in the periodic table of the elements has 12.01. That is the atomic mass of carbon. The atomic mass is the average mass number weighted for all of the isotopes of that element found naturally. So we've already discussed that carbon can exist as carbon-12, carbon-13, or carbon-14. There is very little carbon-13 and carbon-14 on our planet. So the average mass number, weighted mass number, of all the different types of carbon atoms on our planet is 12.01. So if you have a carbon sample, you probably have a trace amount of carbon-13 and carbon-14 in that carbon sample. So the average atomic mass of carbon is 12.01. This goes to show you how that was calculated. The majority of carbon is carbon-12. 1/100th of carbon is carbon-13, and 1/1 trillionth, or whatever that massive number is there, is carbon-14. So there's very little of it. So most of our carbon, again, is carbon-12. We have a little bit of carbon-13, a little carbon-14. So the average mass, or the weighted average, is 12.01 AMUs. And I will never make you guys calculate the weighted average or calculate atomic mass for this class, but I want you to understand why, if most carbon has a mass number of 12, why isn't this number exactly 12? It's because there are different isotopes of carbon, and this is the weighted average. So this gives you the best representative way to calculate how many carbon atoms you have for a given amount of material present. So now we're going to talk a little bit about nuclear chemistry. Before I dive into this, I want you to pause this after I ask you this question here and give this a little bit of thought. When you hear the word nuclear or radiation, what comes to mind? Just think of a few things that come to mind. So go ahead and pause it. Most of the things that people write down are not positive things when they think of nuclear or radiation. We think of the atomic bomb, we think of nuclear waste, we think of Chernobyl, we think of the nuclear energy facility that went down in Japan several years ago that leaked nuclear waste. Now, let me tell you, it was a minor amount of nuclear waste. The news reported that nuclear waste was detected off the coast of California, and that's because nuclear material is really, really super easy to detect, even at levels way below where it could do us harm. So one of the things I want to point out in this chapter is that nuclear chemistry isn't nearly as scary as most of us have. We all have this idea in our head that nuclear chemistry is this horrible, scary, frightening thing. And it's really going around us all day long in our lives. Every time you eat a banana, you're taking in radioactive potassium. Our bodies are equipped to handle a fair amount of nuclear radiation because it exists in the world around us. Any rock can contain uranium, and so you could be getting a small amount of radiation from uranium. In fact, in 1986, this guy Henry Becquerel was kind of one of the pioneers in nuclear radiation, but he got an exposure on a photographic plate by placing the plate next to a rock that contained uranium. So it's kind of an accidental discovery, as many things are in the sciences. So any element that can emit radiation is said to be called radioactive materials. So we'll talk about what makes a material radioactive in just a second, and talk about radioactive formula, or how we balance radioactive equations. So here are some facts about radioactivity and radioisotopes. Most naturally occurring isotopes have a stable nucleus and are not radioactive. So for example, if you take a look at your periodic table of the elements again, we mentioned that most of carbon on the planet is carbon-12. So carbon has that atomic mass of 12.01. The reason for that is that the most prevalent form of carbon has a very stable nucleus. It has 6 protons and 6 neutrons, and that happens to be a very stable ratio of protons to neutrons. As you add more neutrons to that particular nucleus, that becomes unstable. Isotopes that are not stable can become stable by spontaneously emitting radiation from their nucleus. This is called radioactive decay. So this is chemistry of the nucleus. That's why it's called nuclear chemistry. So there's a change to the nucleus to make the nucleus more stable. So that's where the term nuclear comes from. Typically we hear the term nuclear and we freak out and we think of a bomb. When you hear the term nuclear, all we mean is that it's happening in the center of an atom. It's happening in the nucleus. In fact, the imaging called MRI imaging or magnetic resonance imaging is actually called nuclear magnetic resonance imaging, but we dropped off the nuclear when it was used in public practice because that word scares people. So we're actually aligning nuclei in your body and allowing them to relax again. And that's how we get an MRI image, by measuring the rate of time at which the nuclei will relax, because nuclei in different tissue types or tissue densities will relax at different rates. So that's how MRI imaging works. It's a nuclear thing. But we dropped off the nuclear, again, because that freaks people out. To come off my tangent there, isotopes that emit radiation are called radioisotopes. So again, for example, we could have 3 different isotopes of hydrogen. There's hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 3 is tritium. That one in particular is radioactive, so that would be called a radioisotope. The other 2 isotopes of hydrogen are just plain hydrogen, hydrogen 1, and deuterium, which is hydrogen 2. It's hydrogen with 1 proton and 1 neutron, and that just is a little heavier than regular old hydrogen, but it's very stable, so it is not a radioisotope. So of the 3 isotopes of hydrogen, only one of them, tritium, is a radioisotope. We can find naturally occurring radioisotopes, and those can be mined from the Earth, or we can prepare them in laboratories by bombarding them with other subatomic particles or different light with different energies. All of the isotopes of elements with a large atomic number above 83 are radioactive. Those materials are naturally unstable. And some lower elements also have radioisotopes. Ones that are particularly relevant are carbon, hydrogen, we'll talk about potassium, phosphorus, that's a very highly used radioisotope, radioactive phosphorus, P32. That one is used to label DNA regularly, and there are other examples of radioactive isotopes that are used in cancer chemotherapy, and we'll discuss those as well in imaging. So what is radiation? I'm just going to draw a little nucleus here. Let's imagine this is an unstable nucleus. This nucleus is unstable, and it's going to turn into a stable nucleus. And in order to do that, it's going to have to discharge particles in order to do that. So it could discharge that particle in any direction. So if we have a big chunk of that material, and let's say we've got a lot of, we'll say tritium, it's at H3 or hydrogen 3. There are a lot of H3 nuclei or H3 atoms with their nuclei in this block of material. Each one of them could spontaneously break down to form a stable compound, and in doing so, it can throw off a particle. It could do that in any direction. So these are spontaneous emissions, and that's why we call it radiation. It can radiate anywhere from this central point of this guy. So the most important 3 types of nuclear radiation that we're going to discuss, is actually a 4th one that I'm going to throw in there at the end here. But the 3 big ones are the positively charged alpha particle, so there's alpha radiation, the negatively charged beta particle, beta radiation, and the neutral gamma ray. So these guys are really important when we talk about nuclear safety, because you need different levels of protection from these guys. We'll talk about, this is a really large particle, this is a smaller, higher energy particle, and this is a much smaller, much higher energy particle. And so you're going to need increasing levels of protection as you go from alpha to beta to gamma. So depending on what nuclear material you may be working with, and we may be working with nuclear materials in the medical field, you'll need to understand, is this an alpha emitter, a beta emitter, a gamma emitter, or can it emit different types of radiation? And then what kind of protection do I need when I am working with this material? That is all very important. Some other common forms are positron emission. A positron is a funny little particle. We talked about protons, neutrons, and electrons, but a positron, think of it as a positively charged electron. It's about the same size as an electron, but he's got a positive charge to him. And we use this in PET scans, so positron emission tomography. So we'll talk about some materials that can undergo positron radiation, how they do that and how it's used in PET scans. We can also additionally have an emission of a neutron, which gives off no charge. There's really no change to the charge of the nucleus there with neutron emission. So in alpha radiation or alpha decay, you have a very large nucleus, and that large nucleus is unstable, and it breaks down by throwing off an alpha particle. An alpha particle contains 2 protons and 2 neutrons. So an alpha particle is often represented as helium-2, 4. Why would it be helium? Because it's got 2 protons. What has 2 protons? Why, helium has 2 protons. So that's one way we could represent an alpha particle. Sometimes you'll also see it represented by the Greek letter alpha. I know it looks like a backwards fish there. That's my Greek letter alpha with my poor drawing skills. So you could say it's alpha-2, 4 or an alpha particle. So this would be a helium nucleus. It doesn't have any electrons attached to it. So this would also be a charged particle. It would have a positive 2 charge. So we'll write that little 2 plus up here. It tells us this has a positive 2 charge. On a test, if I ask you what an alpha particle looks like, you don't have to give me that charge if you don't want to, but if you throw it up there, that's great. What I'd be looking for is either the alpha with the 4 up here and 2 here, or this here with the helium with the 4 and the 2. So again, the 4 up top here, what's this? This is our mass number, atomic number. So when we're talking about these radioactive materials, we're using the same symbolic symbols as we would use for elements. So that is an alpha particle. It's a pretty large particle, and so you're going to need less of a barrier to protect yourself from this particle. This guy would be absorbed by a very light barrier. Sometimes you can even just use aluminum foil to protect yourself from alpha particles. Your skin is a pretty good barrier as well. So you'd have to have a really strong alpha source to hurt you. Or you might, if you ingest an alpha source, now you're in trouble because there's no protective layer. We have our skin as a protective layer on our bodies, but there's no protective layer for your insides. So your stomach, your esophagus, and your intestines, you have very sensitive cells immediately on the surface there. So ingestion of an alpha emitter is the most dangerous exposure route for alpha emitters. Beta particles are much smaller. A neutron may eject a high-energy electron called a beta particle. And that's represented by the Greek letter beta, so we could have this Greek letter beta. And this guy doesn't have any protons. So what are we doing with this atomic number down there? The atomic number is the number of protons, right? Well, we don't have any protons, but electrons have a negative charge. So from a charge perspective, they're the opposite of a proton. So we put a -1 down there for the atomic number for this thing. And that's going to help us in balancing our nuclear equations. Electrons have no mass. They do have mass, but it's very, very small. So it's very small compared to a proton or a neutron. So we're going to use a 0 there. So for our mass number, for a beta particle, it's going to have 0. For our atomic number for our beta particle, it's going to have a -1. When a neutron breaks down or gives off a beta particle, it becomes a proton as a result. So let's just take a look at that. A neutron would have an atomic number of 0 because it doesn't have any protons. It would have a mass number of 1. So if a neutron broke down, it would become some material, it would give off an electron with a -1 here and a 0 here. In order to balance this, I have to balance the mass numbers. The mass numbers on the left side of this arrow have to be equal to the mass numbers on the right side of the arrow. So I've got a 1 here. I've got a 0 here. I'm going to add a 1 right here. That makes the left equal to the right. My mass number is now equal on both sides. Down here at the bottom, now my atomic numbers have to be equal. I have 0 here. I have -1 here, so I have to give a +1 here to make my atomic numbers balance out. So what is something with an atomic number of 1 and a mass number of 1? Why, that thing is a proton. So when a neutron gives off an electron or a beta particle, it's a high energy electron, then it becomes a proton. So if a material has too many neutrons, let's take a look at that carbon-13. Carbon-13 has an unequal amount of protons and neutrons. It has 1 more neutron than it's supposed to have. Oh, let's use carbon-14. I apologize. We'll use carbon-14. Carbon-14's got way more neutrons than he needs to have. He's got two more neutrons than he needs to have. So if he emitted a beta particle, he would gain a proton and lose a neutron. He'd still have the same, and we'll show you a better example of this. But if this undergoes radioactive decay, it gains a proton, loses an electron, the mass number stays the same because the neutron just got converted into a proton, so the number of protons plus neutrons has not changed. The total number has not changed at all. But now you have something with an equal number of protons and neutrons. You have 7 and 7, which give you the 14. So this is a more stable element. So carbon-14 breaks down to give you nitrogen-14, and this is the guy that we use for carbon dating. I might have said carbon-13 earlier. This is the guy we use for carbon dating. So our third type of radiation are gamma rays. Gamma rays are just high energy light. That's all they are. So they're high energy radiation. It's a high energy photon. The gamma ray is represented by the Greek letter gamma. We represent that with our symbolic notation that we've been using that gamma. And it's a photon, so it has no protons, no mass, so it's just gamma with a 0, 0. And so it's really easy to balance gamma equations because nothing changes. It just becomes a lower energy material. So radioactive materials can become very excited or very high energy, at which point they might undergo gamma decay, where they give off this very high energy photon. Gamma rays are higher in energy than X-rays. So if you think about how dangerous it is to be exposed to X-rays constantly, gamma rays are far more dangerous than X-rays. They have higher penetration power. They can hit they can excite electrons, protons, and neutrons in your molecules that make up your body and do funny chemistry and give you cancer and or just flat out damage tissue. So chronic or rapid exposure to gamma rays can be quite lethal. Exposure to any of these things in the right concentration can be lethal. A positron, we said a positron has the same mass as a beta particle, but is positively charged, and this is wrong. This again came from Pearson, so there should be a little positive down here on this guy. So this is a positron, same mass as a beta particle, but positively charged. It's represented as an electron with a +1 on the bottom down there. This decay will change a proton to a neutron, and it will emit a positron. So if we have a proton here, proton has a 1 here, a 1 here. If it gives off a positron, we balance that by saying we have a 0 and a 1 there. So this is balanced. You can see that the top on the left, the mass numbers are all equal to 1. The sum of the mass numbers on the right, we have 1 plus 0. That's equal to 1. And then the sum of the atomic numbers on the left is 1, and the sum of the atomic numbers on the right is 1 plus 0 is 1. So we're balanced. So proton can break down into a neutron by giving off a positron. So that would be positron radiation. So all of these radioactive emissions that we've discussed, they contain a lot of energy, and they can bump into atoms in your body or into other materials and do crazy chemistry. So alpha and beta particles, neutrons, gamma rays, and X-rays, they're all forms of what we call ionizing radiation. When they interact with another atom, they can eject one of that atom's electrons. That can kick off an electron. Now what was a stable atom before is now reactive. It's less stable. It's going to want to react. So if that happens to a protein or to like a lipid or something along those lines, that damages the cell. That damages the body of the cell. If that happens to your DNA, that damages the blueprint that tells the cell how to repair itself. So damages to the cell can be lethal immediately if you have enough of them. So you can do immediate damage to the tissue with radiation if you're exposed to enough of it. If you're exposed to a small amount of radiation over a longer period of time, you could damage the DNA to the point where the DNA is no longer the right sequence, and that could cause mutations which can lead to other diseases like cancer. So either small or large doses can lead to cancer. Most often it's a chronic low dose that people are unaware that they're receiving that's going to lead to cancer. Or you could also have a very large dose at one time that could damage DNA and also lead to cancer, but that typically doesn't happen unless you're working with concentrated radioactive materials. And in this day and age, you should be aware that you're working with concentrated radioactive materials. A great example of that is we use radioactive materials to kill cancer cells because cancer cells replicate faster than normal cells. We know that radiation attacks the DNA, and when a cell is replicating, it is copying the DNA. So fast replicating cells will die faster than normal slow replicating cells. So you can selectively target cancer with radioactive materials and kill the cancer. There is a chance that you will give your patient a different type of cancer from the very radioactive treatment that you were using to cure their cancer in the first place. The benefit is they probably won't develop that cancer for some time, and you've extended their life by killing that initial cancer in the first place. There's a lot of research on targeted therapies, so we can target the radiation to only hammer the tumor, or we can deliver that drug or that radioactive material so that it accumulates only in the tumor or cancerous material and doesn't do so much damage to the rest of the body. And that's where a lot of cancer therapy is going here. Biological effects of radiation. The higher energy, the further it can penetrate. We mentioned that alpha particles were fairly low energy. Beta particles become more energetic. Gamma particles are the most energetic. So when you're working with radioactive materials, you should have a good awareness of what personal protective equipment you need to protect yourself. If you are working with an alpha or beta emitter, you should have a heavy lab coat, lab glasses, gloves. You'll probably be standing behind a plastic or lead shield to protect yourself. The lead shield is absolutely required for gamma radiation. People who routinely work with radioactive materials or X-rays, we're going to wear a film badge, and that film badge is going to monitor your total exposure, so that after a certain period of time at work, you're going to turn in that film badge, and they're going to determine how much radiation were you exposed to, and was this amount of radiation dangerous for you, and do we need to improve on your personal protective equipment or gear that you're using at work to protect yourself. So this just shows you a good example of how these particles can penetrate and attack you. We mentioned alpha particles. Your skin is a fine barrier. That alpha particle is going to hit your skin. It's going to be absorbed by the dead cells on the skin. It's going to do some chemistry, but those are dead cells that we have as a protective barrier on outside of us, so it really doesn't matter. A beta particle can easily pass through skin, bone, other materials. You need a good You can use aluminum foil or aluminum shield. We sometimes also will use like a plastic shield, a thick plastic shield will absorb beta particles and provide us protection. So you want to be behind that aluminum shield. Gamma will penetrate even aluminum. We have to use a heavy lead wall. Maybe you can have lead bricks or something along those lines, or a lead pig to protect us from gamma radiation. Neutrons can really penetrate some of these other materials. Not such a common thing to be emitted as neutrons. Mostly you'll be working with alpha, beta, and gamma. These are the guys that you have to worry about. So you have to understand, what is the nuclear material I'm working with? What kind of particles does it give off? And what kind of PPE do I need to protect myself at my workplace? Just to reiterate that, some of the common properties of ionizing radiation: alpha particles don't travel very far through the air. They only go a few centimeters. This is because they can react with the air. They're a pretty large particle. They're going to bump into like nitrogen or oxygen or something along those lines and react. So they're not going to travel very far. If it hits you, it's going to stop at the skin surface. It's usually only dangerous if inhaled or eaten. And the reason, again, being that you have a protective layer on the outside of your body, but not on the inside of your body. Paper or clothing is fine protective shielding for alpha particles. Beta particles can travel a lot further. They can travel several meters. So you have to be careful when you're working with beta particles, because not only can you be exposing yourself, but you could be exposing other people around you. So you have to care about where is my shield relative to the other people in the room too when you're working with beta radiation. It typically will not penetrate past the skin layer, but it can do some damage to your skin. It can give you skin cancer and things along those lines. So we really want to be careful still when you're working with beta particles. So heavy clothing, plastic, aluminum foil, heavy gloves, lab gloves, things along those lines will protect you from beta radiation. X-rays penetrate several meters as well. These penetrate tissue, but not bone. So we're going to use a lead apron or a concrete barrier typically to protect us from X-rays. Gamma rays will travel several hundred meters. They are photons, or high energy photons. Before they hit another particle and become absorbed, they can travel quite a distance. These will fully penetrate your body, bone, and everything. So if they happen to bump into something, they are going to do chemistry. They're going to excite different electrons, protons, neutrons, whatever they hit in your body, and those can do damage and anywhere within your body, because they can fully penetrate your body. So we need a thick lead, concrete, a layer of water. Water is a very dense material, so sometimes water is used. In fact, I work with I'm a hazmat technician for the state of Ohio, and one of the things that they teach you when you take the hazmat technician training is, if you encounter a radioactive material and you do not have any safe place to put it, one of the best things that you can do is drop it in a bucket of water, or set a bucket of water on top of the piece of radioactive material, and get people as far away from it as possible. So if there is a spill or something along those lines, and it's a solid that you're dealing with, you can easily contain that thing by throwing it in a bucket of water. And that is a good way to start protecting people in the room if you can't just evacuate the area. We're not going to go too much into radiation dosing in this particular class. If you're working with radiation at your workplace, they will be required to give you a radiation safety training, in which case they will discuss dosing in further detail and discuss what your permissible exposure limits are and things along those lines at work. But just to make you familiar with some of the terms, one of the terms that we use is a sievert. And really, if you're exposed to sieverts, you're being exposed to a lot of material. We're typically exposed to millisieverts. The average annual dose is 6.2 millisieverts. We are exposed to a very small amount of radiation when we do things like taking a transcontinental flight. You're exposed to 0.02 millisieverts. The airport X-ray scan delivers 0.0009 millisieverts. That's 0.9 microsieverts. That's a really small amount of radiation. This is an amount of radiation that your body can handle. Now, it's a small amount of radiation. It could still damage your DNA, but remember, our body can fix small amounts of damage to our DNA. If you're exposed to a very large amount of radiation, our body's repair mechanisms for our DNA cannot keep up. So if you're exposed to way more than the 6.2 millisieverts per year of radiation, your body's natural repair mechanisms might not be able to keep up with the damage that's being done to your DNA, and that's when you're going to start to develop diseases such as cancer and things along those lines. So I've already given a few examples of nuclear equations, but this is how we balance nuclear equations. This is one example here. So this is the breakdown of uranium-238. Uranium-238 is the stable uranium. Uranium-235 it's still radioactive, uranium-238. Remember, it's got an atomic number above that magic number 83, so all these guys are radioactive to some degree. But uranium-238 is not the type of uranium that's used in nuclear fuel. It's present, but uranium-235 is the guy that we try to concentrate or make to get enriched uranium. But this guy, uranium-238, it still breaks down via alpha emission. So if you notice here, we have our nuclear equation. So the left, these are our reactants. These are the things that are going to react or break down into our products. So you got your products on the right side here. So uranium is an alpha emitter. It's going to give off an alpha particle. Uranium has a mass number of 238. We'll notice that the sum of the mass numbers on the other side are equal to 238 because this is a balanced equation. Our atomic number is 92 on this side, and the sum of our atomic numbers on the other side adds up to 92, which is what makes this a balanced equation. So we have to look at our atomic numbers and our mass numbers and make sure that everything's all balanced when we're looking at these nuclear equations. So let's do an example of how we write and balance a nuclear decay equation. We'll use alpha decay here for our example. The first thing we're going to do is, for step 1, write the symbolic notation for the radioisotope undergoing decay. Our next step is we're going to place the ionizing radiation on the product side of the equation. Our third step is going to be determine the missing product radioisotope. Remember that mass and atomic numbers must be equal on both sides of the equation. So let's use radon as an example. Has anybody had their basement tested for radon? Radon is number 86 on the periodic table of the elements, and its symbol is Rn. So I said it's number 86, so its atomic number is going to be 86. The most common isotope of radon is radon-222. So we've got 3 2s up here. My terribly drawn 2s. Please forgive my bad 2s. So that is our first step. Write the symbolic notation for the radioisotope undergoing decay. So that's going to break down, and that is going to be alpha decay. I would tell you in the problem that it's an alpha decay. You'd have to know what an alpha particle is. We're going to use our alpha symbol. You could also have used that helium symbol as well. I don't care which one you use. We know that we have a 2 here and a 4 here because it's a helium nuclei. It has 2 protons and 2 neutrons. So its atomic number is 2 and its mass number is 4. That's 2 plus 2 for the 2 protons and the 2 neutrons gives us the 4. We have a mystery element. This radon is giving up this helium, this alpha particle, and it's going to become a new element now. It's losing 2 protons, so it has to become a new element. So the atomic numbers on the reactant side and the product side have to add up to the same thing. So we have 86 here. We have a 2 here. To get 86 on this side, we have to add 84 to this. 84 plus 2 would give us 86. We have a 4 here. A 222 over here. 222 minus 4 gives 218. So 218 plus 4 would give us our 222. So you can see here, 218 plus 4 is the same as 222. 84 plus 2 gives us our 86. All right, so what is this X? 84, 218. What is that element X? How do we figure that out? We look at the atomic number. The atomic number dictates what element we're working with. If we look at number 84 on the periodic table of the elements, that guy is going to be PO, polonium. So it's polonium. We'd write 84, 218. So that would be our product, polonium-84, 218. We'll do more examples, so you would just replace this part of the equation with that. So to show the full equation, you'd have this radon 222.86, you'd show the polonium 218.84 plus your alpha particle with your arrow in the middle there, and that would be your final nuclear equation. We'll do plenty of examples of that in class. So we can do another quick example here. So we've got phosphorus 32 is going to be a beta emitter. So phosphorus has an atomic number of 15. And we're saying we have phosphorus 32. So this is a really important little isotope that is used to label DNA. DNA has this phosphate backbone. So you can label your DNA with P32, and then you can detect even small, tiny quantities of DNA, and we can use that for DNA sequencing and all sorts of crazy things. So a lot of technology that's done using DNA imaging can be done with radioactive phosphorus. So DNA gels and things along those lines. So this is going to break down into some mystery element. We said it's a beta emitter. I would tell you it's a beta emitter. So it's going to give us our beta particle. I'm going to use the E. You could also use the Greek beta. We know that it's an electron, so it has a -1 for the atomic number. And it has no mass. It's got no mass number, so that's 0. So to balance things here, I have a 15 for my atomic number on the product, on the reactant side. So on the product side, I have to total up to 15. I've got a -1 here. So I need 16. 16 minus 1 would give me 15 for my atomic number. So that will add up. I've got a 0 here, which means I don't have to change my mass number. So I've got 32. So what's my mystery element, X? If we look at the periodic table of the elements, the guy who has an atomic number of 16 is sulfur. So our final equation would look like this. We'd have P15, sorry, not P15, phosphorus 32 with an atomic number of 15 goes to, reacts to make sulfur with an atomic number of 16 and a mass number of 32 plus our beta particle, our electron with a -1 atomic number and a 0 mass number. All right, so balancing equations for gamma particles is like the easiest thing that you've ever done, because gamma particles don't have an atomic number and they don't have mass numbers, it's 0. So what happens is you have an element in its excited state. This is radioactive isotope in its excited state, and we'll show that by using this little M. So this is technetium-99M. So this is a radioactive isotope that is used for imaging. We use this for a lot of different imaging purposes. This has an excited version of technetium-99. It decays by giving off a gamma particle. That gamma particle is then detected by some type of imaging film or by a detector. It decays to a stable isotope, technetium-99. So nothing really changes. So gamma is the easiest thing to balance, or the easiest equation to write up, the easiest equation to balance. So how do we get radioisotopes in the first place? If they're constantly breaking down, if they've been breaking down for billions of years, since the dawn of time, or shouldn't they have all broken down by now? And the answer is that there's a lot of chemistry that goes on in stars and things along those lines. Our suns and our universe constantly giving off radiation, and that radiation can hit stable isotopes and convert them back into unstable isotopes. So for example, we talked about carbon-14. Carbon-14 is used in carbon dating. It turns into nitrogen-14, floats up in the upper atmosphere, and it's bombarded by radiation from the sun, turns back into carbon-14, and then we breathe it in, or our plants bring it in to make sugar from CO2. And then we eat the plant and take on carbon-14. So there's a cycle for some of these things. So you can make radioactive isotopes in the lab as well. So we can bombard them with fast-moving alpha particles, protons, or neutrons. We use that ionizing radiation to make an unstable isotope. So an example here is we're converting stable molybdenum-98 to an unstable version molybdenum-99 here by bombarding it with a neutron. You'd have a neutron radiation source, and you'd hammer it
and add that neutron to that nucleus of that molybdenum. So there are a few other radioactive units that I just want you to be aware of. We measure radioactivity of a material by the number of radioactive emissions in a second. So one type of unit you might see is the Curie. So that's a measure of how radioactive or how hot something is. You might also see the Becquerel. I think in the United States we tend to use the Curie more often than we use the Becquerel. So that might be something you'd see. So again, this just to give you an idea of how many disintegrations per second are happening with the Becquerel. Becquerel is a standard for 1 disintegration per second. A Curie is some large number, 3.7 times 10 to the 10 disintegrations per second. It's a little bit easier to measure because it measures a large number of disintegrations. Most often when you're working with pretty hot radioactive material, it's going to be in the millicuries range. If you're in the Curies range, you're really, really radioactive. And then microcuries is going to be far less radioactive than millicurie. Of course, you're 1,000 times less radioactive. You have fewer disintegrations per second. All right, let's talk half-lives. So not all radioactive substances or radioactive isotopes give off these particles at the same rate. Every radioactive isotope emits radiation at a particular rate based on what that thing is and how unstable it is. The more unstable it is, the faster it's going to emit that radiation. So really unstable things are going to have a really short half-life. They're going to break down really fast. We call this rate of decay a half-life. It's the time it takes for 1/2 of the atoms in a sample to decay. So you might hear the term half-life or physical half-life. This is different from the half-life that's used in medicine. Sometimes we call the rate of elimination from the body the biological half-life. So still the same definition. It's the time it takes for 1/2 of something to be gotten rid of. So if you're talking radioactive half-life, we're just talking about a sample sitting on a table. So how long does it take, if you have phosphorus-32, for example, how long does it take for half of that phosphorus to break down? Now, as that stuff breaks down, that block of phosphorus, let's say you've gone through 1 half-life, there's only half as much radioactive material in that block of phosphorus now. That block's not quite as unstable as it used to be. So it's actually going to start to slow down, and so you'll see that if you've gone through 1 half-life and you've lost 50% of your radiation, you would think that if you've gone through a 2nd half-life that you'd have no radiation left. But that's not what happens. It just gets cut in half again and again and again, so that it seems like you'll never quite get rid of all of the radiation. So as time goes on, the rate at which that radiation breaks down or gives off radioactive decay slows down. And that's why I have to use this term, the half-life. So I'll give you an example of what that equation looks like and some examples. In class, I'll draw on the board the curve for half-life, and we'll do some example problems with half-life. So most naturally occurring radioisotopes have really long half-lives. They're not very dangerous. They have really long half-lives. So for example, carbon-14 has this huge half-life of 5,730 years. So it's a pretty stable guy. We've got carbon-14 in our body. You shouldn't be scared about it. Yeah, sure, it's a beta emitter. Beta particles are dangerous and everything, but how fast is it breaking down? Every few thousand years, give off a few particles in you. It's not a big deal. So that's one of the reasons why we can use carbon-14 to date things, because it takes so long to break down. You can measure what's the percentage of carbon-14 in this material that's thousands of years old, and there will still be some carbon-14 in it. It won't be the same percentage as a human being that's still constantly taking in new carbon-14 through their diet, or any live organism. It's going to have so if something's been dead for thousands of years, it's going to have a lower ratio of carbon-14 to carbon-12. And that long half-life is what makes it so useful for carbon dating. Some things that are used in medicine are a lot more dangerous. So for example, chromium-51 is one of the things that's used for cancer chemotherapy, and that has a half-life of 28 days. Now, this is nice if you get contaminated with the stuff because you know that you're not going to be radioactive for the rest of your life. You know, after 28 days later, you only have half as much radioactivity in that particular sample that was, and of course, biologically too, your body's also going to be clearing a lot of this stuff. So it's going to kick it out of your body through your basic digestive process or clearing processes like your kidneys and your liver and things along those lines. But if you have this stuff sitting out on the shelf, its half-life is pretty short. So if you start out with 1 gram of radioactive chromium-51, 28 days later, half of that will no longer be radioactive. So you'll have 0.5 grams of chromium-51. Another 28 days later, you'll have half of that. You'll have 0.25 grams of chromium-51. You see how that decay slows down. So as we keep going, we're going to, with additional half-lives, we're going to keep cutting that material in half until you effectively don't have any measurable quantity of that material. So the formula for determining how much material we have based on the number of half-lives that have gone by is we take the starting amount of material, we multiply that by 1/2 raised to the power n, where n is the number of half-lives that have occurred. So if I tell you that our half-life is 3 days, we have a half-life of 3 days, I tell you we start with 1 pound of radioactive material, and I tell you that 6 days have gone by. How much of that material do we have left? We start with 1 pound. We multiply that by 1/2 raised to what power? N is the number of half-lives that have gone by. 1 half-life is 3 days. So we take 6. We've had 6 days divided by 3. That gives us 2. So 1/2 squared is the same as saying 1/4. So if we started with 1 pound of this material, we now have 1/4 of a pound of this material, 0.25 pounds of this material. So that's one example problem for half-life. We'll do more of those in class if you didn't follow me there. So how do we use this medically? One of the most common ways that we use radiation in medicine is for imaging. So nuclear radiation is given off in these high-energy particles or high-energy rays. Some of these are useful because they can concentrate in particular tissues. So we could, for example, give a radioactive version of iodine, and that could concentrate in a healthy thyroid. Your thyroid gland takes up iodine in your body. So if you had a radioactive iodine, we could then image the thyroid. Additionally, you could use like a photographic plate behind the body, and you could expose someone to nuclear radiation that only passes through certain types of tissue. Say for an X-ray, you could pass X-ray, which is a form of radiation, and that won't pass through your bone and other dense materials. So you can develop an image along those lines using that technology. So there are different ways that we can use radioisotopes for medical imaging. So here's one example for a medical application of a radioisotope for imaging. So they take xenon-133, and you can check this out in your book on page 67. Xenon-133 is a gas that can be inhaled into the lungs. It's a radioactive isotope, so you can inhale this radioactive isotope and then take an image quickly. Any portion of the lung that is unable to take up that radioactive isotope is damaged somehow. So this is a perfect example of using xenon-133 to image the lung to detect lung cancer. So this poor person has a tumor in this dark spot here, and this is necrotic tissues. This lung is not functioning properly in this area and could not take on the radioactive gas. Now, of course, we're not using this radioactive gas in a high enough dose to give you lung cancer. You can detect very small quantities of radiation. So that's one thing I want people to be aware of. When we're exposing patients to radioactive materials for imaging, we're not endangering the patient with large doses of radioactive material. As I said before, it is very easy to detect radiation. We can detect radiation at doses that are far smaller than would cause the body serious harm or damage. You won't feel any physical side effects from one application of this Xenon-133. Now, if you did this constantly, day in, day out to a person, of course, you could do some damage there. But this is safe technology here. That being said, it's important that we keep in mind that this stuff is dangerous if you expose patients to too much of it. So it's very important to expose patients to the smallest possible dose of radiation and expose them for the shortest time period. We protect ourselves in several ways. You can use time, distance, and shielding to protect yourself from radioactive isotopes. The patient can't run away from the material, so distance is kind of out. We can use shielding for different parts of the patient's body. If it doesn't have to be exposed, you can use shielding for yourself, and you can decrease the amount of time. You can also decrease the dose for the patient. So we're going to use the lowest possible dose for the shortest amount of time, and we're going to shield the patient and ourselves, of course, if we can. We're going to try to select radioactive isotopes with short half-lives for the use in nuclear medicine. This is so that the stuff breaks down rapidly. That way, if it does accumulate in the body, it's not going to be constantly throwing off radioactive material in this person. One example is iodine. It does accumulate in the thyroid. So we want to use something with a relatively rapid half-life so that even if the thyroid is accumulating that, it's going to break down into something stable that's not going to do that patient any harm in the long run there. So we'll show a picture of that radioactive iodine being used, iodine-123 here on the next. So this radioactive iodine, or iodide-123, is used for thyroid imaging, and this can determine whether or not the thyroid is healthy. So here we've got a little cold spot here. This is a nice healthy thyroid. You can see that the gland on both sides of the neck, similar shape and size on both sides. The tissue is healthy and was able to accumulate an equal amount of that radioactive iodine on both sides here. We got a little cold spot here where this is an unhealthy piece of tissue here. So that's going to give the doctor some clue as to the health of this patient. So to elaborate on that, if you've got a non-functioning area of the thyroid, it could show up as a cold spot, so it's not going to be able to take up that radioactive iodine. If you have a spot that takes up way too much, that could be showing that there's rapidly dividing cells. So that could be cancer. That could show up as a hot spot. Additionally, we can use radioisotopes to destroy diseased tissue. So we could use a more energetic form of iodine, so iodine-131, a beta emitter, and that could be used to treat thyroid cancers. Again, cells that are rapidly dividing have more exposed genetic material. So they're constantly replicating their DNA, and these cells are destroyed at a higher rate by radioactive compounds. This is one of the reasons why we use radioactivity to treat cancer. Some of the other cells in your body that divide very rapidly are your white and red blood cells, your hair follicles. So this is why in your gut, the lining of your gut, actually, the lining of your intestine replicates pretty rapidly. And so this is why we have some of the very common side effects of nausea, your hair falling out, white blood cell count dropping. These are side effects of cancer chemotherapy. And targeted delivery of the radioactive material is one way that we're trying to circumvent these negative side effects for these patients. So there are a few different ways that we can administer cancer chemotherapy. So you can use an external beam radiation therapy. So we have a beam that is focused in on the tumor. So we aim, and essentially you're using a radioactive laser beam and hitting that tumor and destroying that tumor tissue. We also have a form of therapy called brachytherapy, in which you can put a small radioactive titanium seed that contains a radioisotope, and that can be implanted in the tumor. So that's going to constantly give off radiation, in that tumor where that thing was implanted, and just kill that area surrounding that seed that's been implanted. So the last kind of imaging that I want to discuss is a PET scan. The PET scans are used to identify functional abnormalities in different organs and tissues, most commonly used for the brain. In this case, we can use fluorine 18, and you can fluorine label many different molecules, so you can kind of determine where a molecule goes in a particular organ, whether it gets taken up or used, by monitoring the emission of these positrons that come off of this fluorine 18. So you would administer some compound that's been labeled with this fluorine 18, and then you can image the fluorine 18 as it decays to form oxygen 18. So the positron comes into contact with an electron, and gamma radiation is produced and detected by the scanner. And so, as I said, this type of scan is commonly used for the brain. So that concludes chapter 2. So we'll do a bunch of example problems in class, and please make sure that you read your chapter and do as many of the in-chapter practice problems as possible.